1, 2, 3, 4. Do everybody hear me well? Okay, hello again, and today we will be solving problems from Polish Olympiad in Informatics. You can see the link in the description. Possibly some of you have already read or tried to solve problems. I've read before this stream 2 hardest problems to make sure that I'm able to solve them. So I know how to solve the first 2, so like Meigs and Kinoman, and the next 3 problems I don't know, but I know they are easy. And we will start from the first problem. I'm not sure if I will be implementing the solutions today. We'll see, maybe depending on the problem. The first problem is pieczęć in Polish, that is seal in English. And let me read it. Okay, and I remember that this problem I saw a few years ago, and I'm not remember if I solved it back then, but I also think I saw a similar but harder problem during one of ACM trainings. Okay, so I think we are given a matrix of some given size, and we are given a smaller matrix, and we ask if we can put this smaller matrix on a bigger one a few times, to like put a few copies of that to get the big matrix. For example, here we can take this shape, this smaller shape, and put the similar shape to the right to get this bigger shape. So in particular, if the smaller shape is just one cell, one X, then the answer will always be yes, because the question is it possible to put the smaller shape a few times so that we would get the bigger one, exactly the bigger one. So if there is one X in the smaller shape, the answer is always yes. If, for example, it's 2 X's next to each other, so one to the right of the other one, like domino piece, then in every row we could greedily put these domino pieces next to each other. So if every row of cells in the big shape is of even size, then the answer is yes. And of course here we have a general scenario where shapes could be more complicated and not necessarily connected. Still, it's good in this problem to think how a human would try to solve this problem. So how you yourself would decide whether it's possible or no. So without any computer, just having this input like this to decide yourself. So maybe paint will be good for that. The problem is seal. For example, let's say that the shape is just, I don't know, sorry, axis. That should be axis. A square of size 2 times 2. Then, if there is some bigger matrix, how exactly would you yourself put these squares on the matrix? Well, it seems stupid to choose some place in the middle and to see whether we can go from this. Usually a human would just start from the left. And when we start from the left, or maybe from the top, let's say we start in the first column, it makes most sense to start from the topmost place there. So maybe here. So I think the most straightforward solution for a human would be to choose, let's say, this place, these 4 cells, to put the first square. Then of course we see that we have a single x here that can't be used in any square anymore. Like, we can't cover this. Also, the statement said the patterns can't overlap. So now we see that the answer is no. And the thing is that we can't avoid putting this square here, because we must cover somehow this cell. So the input was this, and the only way to cover this exact cell is putting the square we've just considered. So the answer is the answer is no in this case. And let's see if this approach would always work. Of course, maybe here there would be no x, so then we put one shape here, and then we can treat this matrix as there would be there would be nothing here in the beginning. So we just replace these places with dots, so with empty places, and we again ask whether we can cover the whole shape with this pattern. And the answer will be no, because of this place. So in the next step, with our human-like algorithm, we will try to put a square with top left corner exactly here. Just like going from left to right, and every time putting as high as you could, because you anyway have to cover that cell, so we can start from that. And this logic makes sense if the shape is nice, like this one, like square. Of course, the input could contain a very strange shape. For example, something like this, not necessarily connected. So this would be the pattern. And what we would do then? Build and compile arguments, so GitHub, it will be easy. Okay, I will figure that out after the stream. I am in class right now, so good luck listening. Okay, so what if the pattern is more complicated, like this one, not necessarily connected, not necessarily in a form of square or rectangle? How to adjust this solution? Again, let's go back to our first big shape. It doesn't hurt to first decide about this cell, the leftmost, rightmost cell, the leftmost, topmost cell. So usually when you have to put some shape somewhere, as I said at the beginning, it's stupid to decide about the middle, because you have no idea what to put exactly here. So this cell must be covered. And of course, since it's the leftmost cell, it must be covered in this pattern by one of the leftmost x's in this pattern. So for sure something in the first column here. In this case, it must be this x. And if there is multiple x's in the pattern, then we must choose the topmost x of them to be here. Because otherwise, if you, for example, want to put pattern in such a way that this bottom x would be here, then this higher x would have to be above this x. while we said this is the topmost x in the first column. So it's impossible. So we know that exactly this x should be put in this place. And after putting, you would get these cells would be covered, and we would turn them into empty places represented by dots, and we would repeat. So we again find the leftmost topmost x, and we must put the same x in that place. And so this algorithm we can easily call greedy. So just find this first spot, we must put something there. We know how we would put it. We turn some cells into empty ones, and we move on. We put the next piece and the next piece and so on. And if there is an error at some moment, we print no. So we print here, we print nie from Polish. And I will move to implementing that. So the goal is to every time find the leftmost x in the big matrix, and to know where is the leftmost x in the small pattern. And of course we want to avoid complexity size of this times size of this, because the constraints are up to 1000. So it's okay to have 1000 square. So the size of one matrix is up to 1000 square, so 1 million, which is fine. But we want to get exactly that complexity, not something bigger. So it isn't correct to every time scan the whole matrix to find the leftmost piece, then to scan this pattern, find the leftmost piece, and put it, because we could do that many times. For example, if this pattern is, let's say, huge and filled with empty places, and except for maybe, I don't know, 2 x's, something like that, then we would have to put this pattern in the big matrix million times, O of size of big matrix. And if every time we scan this pattern, we would get complexity size of one matrix times size of pattern. That is too big. So instead, we must do it faster. So I think it's a good idea to scan the pattern once. So we already know where is this leftmost x, and with respect to it, where are the other x's. So we know that this x is here, and that this x is 4 cells to the right and 3 cells down from this one. And we don't have to read the whole matrix again or start in linear memory. We just remember positions of x's with respect to the leftmost one. And what about the big matrix? So again, we don't want to scan it every time, but what we can do is to just choose some order of cells. So let's say we have something like this at the beginning. We go in some order. So first we consider this cell. We wonder whether there's an x there. Then this cell, and yeah, we notice x. So at this moment, we say that we put one occurrence of pattern here. So this x will turn into dot, into empty cell, and the same with this x, because we know that the other x was in some position with respect to that. And we don't start from the beginning. Instead, we just move to the next cell, and we consider, should we put pattern here? So we will just once go through the matrix in this order. So first column, then second column from top to bottom, and so on. And every time, if there is an x in this cell, we know that it's the leftmost x. We must put pattern here. So in linear time, we turn some cells into empty cells, linear of the number of changed cells. So in total, the complexity can't exceed the size of the matrix here, because with every extra operations, with every extra operation we turn one x into an empty cell. So the complexity will be scanning through the whole matrix plus the number of x's. So the complexity will be fine. That might not work, right? I don't know why that wouldn't work. And okay, we can implement that. We have Q test cases in this problem. I prefer to use T for that. Okay, and let's use scene. You must use these two lines to make scene and cout fast. It's good to extract the test case procession into a separate function, not to have everything in main here. Now, if you just have a function here for one test case, you don't have to worry about, I don't know, clearing things between different test cases. You just have to focus on this one. So it's generally a good practice to create functions wherever possible, because when they do something completely separate. Okay, we read dimensions. I like to call them h and w, like height and width of a grid. And now we read them. First there's that big grid, and then there is pattern. Of course, because I named it this way, I must be careful about uppercase and lowercase, especially W. Maybe it wasn't a good idea to name it W because the small and big letter are very similar. But let's go with this. Now, we want to once process the pattern and find the leftmost x and positions of other x's with respect to that. Okay, and the question is also whether it's possible that there will be no x's. Let's see that. Contain a trace of ink. I guess it means it's guaranteed that at least one cell contains X. I'm not sure about this wording. Let's go with that. Okay, so how to call it? Let's say that the leftmost pair will be some pair. Maybe it isn't necessary. We need a vector, so kind of a list. Like it's more common to use a list for that, but vector is also fast and it can do more things. So let's create a vector of pairs that will describe the positions of x's here. So I don't know, let's call it positions. And now let's iterate over a column first, then the row, because we first prioritize leftmost. And if in pattern of row call, row goes first, because we've read row by row, if this cell is X, then we do something. Here we know that row call is the position of the leftmost X in pattern, and let's now iterate over all the cells in the matrix. And for example, here we knew that the position of the leftmost x was 0, 1. So 0 means, so maybe it's better to name it 1, 0. 1 is because it's row number 1, and 0 because it's column number 0. And this x had coordinates 4, 4. And then we just will have to subtract it to get coordinates with respect to the first x. So this would get then coordinates 3, 4, because it's the 4, 4 minus 1, 1, 0. So now I will iterate over all the cells. Let's say that R2 means like row to row of that other cell. And we add something with like this subtraction. So R2 minus row, and let me move it to the next line, and C2 minus col. And you can notice here that I also here will add that leftmost cell itself. So I would also put 0, 0 in this positions vector, and it's fine, because what I want to gather is positions of everything with respect to the leftmost x, to know what cells I should turn off. And this cell will be also turned off itself, so it's fine. Okay, we did that, and now we must go through the big matrix. Are there any questions now? If the first matrix is filled with x's, then don't you think the complexity would increase? No, I explained why the amortized complexity is 1000 square, because one more thing here is, of course, that we should break from this whole thing, because if we found the leftmost x, we put everything in positions, and now, okay, here we've created positions vector of pairs, and now we should break. And writing break here will not be enough, because it will only break from this 4, and we could use go to, what is quite ugly. I will also do something quite ugly. I will change call to w to also get back from this loop. It's some hack. Hi Bartek. The complexity for each case will be r times c. Yes, so Anish here repeated what I've explained about the amortized complexity, about the part that I will implement right now. So now we must go through the big matrix, and as we've told, we again want to go column by column. So first we iterate by columns, and now we go up to big W. And if the big matrix, what I called, I think, grid of row col contains an x, then we do something. And what do? We must turn off some cells, because we noticed, for example, we found this x, and we must put some pattern here and turn off some cells. And those cells will be p in positions. So this is equivalent to iterating over index of this in this positions vector. But this is how you write it write it more like easier in modern C++ or Java. And here what we want to do is grid of row plus p first, call plus p second, turn to dot. And there will be some issues with that. It's correct in terms of putting pattern in a wrong place. So we start from position row call, and every this respective position, respective vector from this cell, we turn off. But also we must check if this position contains an X. For example, for this pattern, if the big matrix just contains, let's say, 1X here, and only empty cells except for that, then the answer will be no, because there should be an X here when we put pattern with leftmost X here. So if there is no X here, we should print no. And here I want to avoid copy pasting and, for example, printing if this is equal to dot then something. So it's better to in C++ to do this, to use ampersand. So how to call it? It's not, it's a reference to a value. And if we write here, let's call it, I don't know, ch, like char, that will be this value. Then from this moment, we can use it instead of the long formula. So it's nice to do it because it makes code nicer and it's harder to make a mistake. So if this value is dot, then we print no in Polish, and we return from the whole function, so the whole test case function, because it's the end of this function. If we will not print no at any moment, then at the end we must print yes. We must print tak, that is yes in Polish. Okay, otherwise, if there was no X, we put no, otherwise we change this cell to empty. But also, this cell might be out of boundaries. So we must also check, let's say, I don't want to print many ifs here, because it will make this place harder to read. So instead I will do if not inside of row plus p first, call plus p second, then also put no. And inside is something that is completely independent on the function, so we can just create a new function for this, and where something is inside. If row is between 0 and height -1, and similarly for column. And here we would also have to let this function know h and w. So here we could pass it or make this global. What I will do instead in C++ is make this function local. What I can do here. But if you don't know how to do it in C++, you don't have to. It isn't important. Okay, so this is the same function, just written inside some other function. And let's remove this, and I think we can compile our function. Links for problem are in the description below the video. and also we can submit later. Okay, it's compiled, and let's run it. I recommend saving input to file, not to copy it again and again. Please tell me if the video starts glitching now. It happened to yesterday at some moment, and I'm not sure if it might be because of this terminal that is called Gwake. So do let me know if the video starts glitching, then I will stop using this terminal. The answer was okay for the sample test, and let's submit that. In this system, in this platform, this information means initial OK, what means that a few tests were passed. It doesn't necessarily mean 100 points. It's like the sample test or something like that. But we got 100 here, so it passed all the tests. And we can also see running times if we need, and it passed, let's say, easily. One more thing I want to say here is the order of loops, what is very important sometimes. Here, for example, so the order of these two loops came from the logic of our program, because we said we want to find the leftmost x, and among those we want to find the topmost. This is why we iterated first over column to prioritize leftmost and then over row. But if possible, in your implementation, in your algorithm, you should use the same order of columns as dimensions of your array, and to get effective and faster use of cache, I think it's called cache. This word. I don't know how to read that. Cache. Okay, so actually doing it in this order, of course, it would change our logic, but it would make a solution, a program faster, not in terms of complexity, but in terms of, let's say, constant factor. And here, of course, we said that no, we must iterate over column first, because this is what logic said. Actually, we could change the logic not to take the leftmost x, but instead to take the topmost x, and among those to choose the leftmost one. And then our program would be slightly faster. So once you're aware about this issue, you should think about it when implementing and when you're worried about getting time limit exceeded. You can ask some questions now about this problem if you have any, and we'll move to the next problem. So I will start already reading the next problem. That is łasuchy, gluttons, and you can also, if you have some general questions about, I don't know, competitive programming or something else, you can ask them. I will read and answer. Bartek Kostka says that changing loop orders in Szkopu in this platform doesn't matter, and yeah, it's possible because Polish Olympiad measures not time but number of instructions, but it isn't true for other competitions like IOI and, I don't know, code forces. So remember about these things, like the order of loops, in all the other competitions. But yeah, thank you, Bartek. I didn't know about that. Can we transpose the matrix? We can, and it will be equivalent to changing in our logic columns with rows. So the program will be slightly faster. Okay, so there are n people sitting around a table, and there is a cake between every two people. So there are also n cakes, but they're like shifted half a place. And every person should choose one of the two cakes next to him or her. If he is the only one to choose that cake, then he gets its value. And otherwise, so if two people chose the same cake that is between them, then each of them gets half the value. We want to find such an ordering, such a way to choose for everybody, so that everybody would be happy with their decision. Everybody would be able to say, if I change my decision now from, let's say, right cake to left cake, I will not be better off. Because if someone would be better off changing his decision now, he would be dissatisfied, as the statement says. And we are asked about like any valid solution, any solution leading to no one being dissatisfied because he should change the decision. And this is a problem I haven't seen before, so I will solve it from scratch. Which is better for practice, Timeless, Online Judge, or Codeforces? Codeforces, because it has editorials. Where can I learn DP problems? Anywhere. Just Google, either choose some platform where you can choose topic DP and learn, like, solve problems from that category, or just Google DP tutorials. Maybe Topcoder has some, I don't know. Okay, so here I think some drawings would be nice. And this time I don't know if I'm able to do that in editor. Maybe I should use Paint. Let's create a new directory. Gluttons. Also a short survey. Where is everybody from? From what countries are you guys? Maybe it will be related to time zone right now. Maybe some people have night, but I think it's, well, maybe for example Europe or USA go to work or school, so maybe there will be more people from the east. Let's see. Moldova, India, Belarus, India. So far, most of the people, at least in chat, are from India. It isn't that surprising. Okay, let's see what we can get with drawing. We have some circle. We have some people. let's say that red dots are people. And between them there are cakes, and of course cakes are described by numbers. Maybe I can do that with black. Okay. So we have majority of India. I will put drawing to the left, not to cover it myself with my face. Let's choose. Well, okay. Let's this 7 represent a cake with value 7. 10, 2. I think it's important to choose much different values at some positions, because maybe 7 and 10 will be something completely different from pair 7, 2. Let's see. The thing is that I would say that this person, no matter what will happen, should choose 7. Why is that? Because even if the next person also chooses 7, then this cake gives 3.5 value to each of them. So this guy should never take 2. So if one value is more than 2 times bigger than the other value, this person can choose this value. Will always choose this value, and we can be sure about that. And that isn't necessarily true. Like, this person doesn't necessarily have to take this. We will see in a moment. And right now, for this person could be sure that this value is 3.5 for him. So he should for sure take a 10. Even if it's halved to 5, it's still bigger. So if one value is smaller than the other one, so 7 is smaller than 10, and it's for sure taken by someone else, then we should choose the next value. For this guy, similarly to the situation here, this guy should choose 10 because it's 2 times bigger than 3. Same here, this guy should choose 9 and this guy should choose 9. So here we managed to find a good solution, I think. We can now check that at every place, every person is not dissatisfied. So this person doesn't want to change to 2, this person doesn't want to change to 3, because they both have 4.5 here, the half of this value. And we can check the same for the other 3 guys. So that wasn't very hard. But of course, so what we got is some set of rules, like if 2 adjacent values are such that one is 2 times bigger, then always choose that one. And here the other rule was, if smaller of adjacent values is already taken by someone, choose the next one. Here it gave us the whole the whole solution, the whole choice, but I don't think it will necessarily be true, because what if all the values are similar? For example, 7, 9, 10. We will not start with anything. So how to do it easiest? I think we can start from an empty circle again and just put different values. So what if here we have 8, here we have 9, and here we have 12. So now none of the rules we used before works anymore. No number is 2 times bigger than the adjacent ones. So we will have to think some more. what if instead of 10 there is at 1? If you're asking about the first drawing, I'm not, like, I don't want to now go back to that, but I think we still have a situation where we have to figure out something new. And it might be easy, it might be hard. Of course, it should be reasonable for people to, like, more likely go towards bigger numbers. So what if some guy, let's say this guy, chose 12? Because what the task is to find one possible scenario, and maybe we should just consider for some person to choose this value, and from this everything else will be like uniquely determined. What then? Then for this guy, we know that he should choose 9 because of the rule before. I think we can, like, write down the rules. So there are 2 rules we used so far. If let's say that x and y are, or maybe a and b are 2 adjacent numbers. If a is bigger, 2 times bigger than b, then choose a, that's for sure, like the situation with 10 and, like, no, situation with 7 and 2. And if a is bigger than b and b is chosen by someone else, then choose a, because it will be only better. So these 2 rules we already can use. And here in our drawing, now if we started from this assumption, like our guess, then from rule number, what rule? Okay, it's a new rule. So for this guy, he for sure should take a 9, because here he can get at most 8 of value. So yeah, we can write that, and it's a new rule, and we can state that if a is bigger than b, or not. So this was the, no, this is a new rule, because for this guy, no adjacent value, no adjacent cake is chosen already. What we have is situation where a is bigger than b and a is not chosen for sure. Then choose a. And here not chosen means this guy already decided to take the other cake, so 9 is not chosen by the other guy. So for sure the value of 9 for this new person will be exactly 9, not 4.5. Similarly, then for this guy he should take 8, because 8 is bigger than 7 and 8 is not chosen, so we use this third rule. And now for this guy, this rule doesn't apply anymore, because he can take 7, but maybe 10 will be free, and so 10 maybe will have value 10. For this guy, 12 has value of 6 now for sure, so maybe 10 should be taken, but maybe 10 will be taken by the other guy. So in that case 12 would be better. So for these two we don't know what to do right now. While I was considering these cases, my other idea, just completely new idea, I don't know if it's better or worse than what we are doing currently, is to just choose some scenario. For example, let every person choose the right cake, and then just improve this thing a little bit. So for every person, in some order, for every person, if right now he should choose the other cake, Then let's make this change. And this maybe will lead to, like, this will be, or not. The question is whether we would keep improving the whole scenario in some way, or maybe we would get into infinite loop. Also, the question is whether this would be fast, so whether we could implement that in O of n, or maybe n log n complexity. I don't know. I think it's better to still examine this approach, but maybe we should later switch to the other one. Any questions? Can anyone name for me what is this problem? Sorry, because I've just been here. The description contains links, and this problem is called sorry, not this problem. This code is called Gluttons. Also, when you enter a link from the description, you should switch the language in top right corner to English. Okay, so we have some free rules. Let's get back to our drawing. And now again, maybe we should just assume for someone to take something. So either for this guy or for this guy. I don't know what is better. Let's say that this guy takes a 10. And then the next guy should take 7. He's the last guy to decide, let's say, and like this cake got value 5 if, like, for this guy. If he instead of 7 chooses a 10, he gets 5. So yeah, it's better for him to choose 7. Right now we can see that the whole drawing became kind of irregular because every person took a cake on his right, or on his left actually, and it turned out to be fine because for every person, if he wants to change his decision, he will get half of the value of the other cake. So here maybe a good approach, good way of thinking right now would be, maybe this often is an optimal solution, one that is valid, correct, and let's prove that this is valid, and because from this proof maybe we will get when this shouldn't work, when we should do something else, or maybe this is a whole solution. So a proof was that if no value is 2 times bigger than some adjacent value, then for every person we can assign right cake for him, like to create this regular shape, because changing from, let's say, some a to a cake with value a to b divided by 2 will not be better if no value is 2 times bigger than the adjacent value. Okay, and if no value is 2 times bigger than adjacent value, we have a solution. Otherwise, we have, from this rule, we have some start already. So let's say that here we have, I don't know, 25. Then we know that in this case both these people should take 25 because 12.5 is bigger than anything else, and we can go from that. In this particular case, now from our rules on the right, we would get that this guy should take this value, this guy this value, so we go on, and this guy can choose either the whole 7 or 8, and he would choose 8. But I think we got a bit lucky here because for this guy immediately we knew what we should do, and the same on the other side, but possibly these two values could be a bit smaller, and then we would do something else. So let's say that this is, I don't know, 7, and this is now 6. So from this moment we can't so easily decide what to do. But maybe for this remaining part, so this part, we can say, okay, so here it's true that no value is 2 times bigger than the adjacent value, so maybe we can use that general pattern for every person to take a cake on his or her right. So to do something like maybe this. So this is almost okay. Well, this is okay, I think. Nobody should switch their decision. But maybe this guy, if this value would be a bit bigger, he would want to switch to a 6. And then similarly, this guy maybe would want to switch for the free cake on his left. So my understanding or my guess is that starting from one side, so in this order, as long as cake is bigger than the adjacent cake, it should be taken. So if this 6 would be instead something bigger than 7, it should be taken. And eventually, because let's say that this value is 16 instead of 7, then yeah, it should be taken. But then let's say that 7 is smaller than the next value, that non 8, and then we can apply everybody taking a cake to the right. It will be fine. So from this, so the following solution happens, makes sense maybe. To first decide about values that are 2 times bigger than adjacent values, and then for the remaining part do something very simple. So up to some moment maybe everybody will take a cake to his right or to his left, and from this moment, let's say value 7 turned out to be smaller than 8, and then everybody takes cake to right. Also, please notice that starting from this moment where somebody took a cake to the right, every next person for sure will take a cake to the right, because taking the other cake, so for this guy to take a cake to the left, would mean getting only half of this value. But we said all the remaining values are such that no value is 2 times bigger than the adjacent value. So I think this will be a solution, or maybe there are still some issues with that, but maybe we will figure that out during the implementation. Implementing sometimes helps to show you what cases are missing. For example, you write some ifs. If A is bigger than 2 times B, then do something, else if A is smaller than B, do something else, and then you see, okay, I don't know what to do in this scenario. And also, my guess right now is that the solution is always possible. Here, the statement said that we should print no, we should print nie if there is no solution, but I think from this we get that all the time there will be some solution, but we'll see. Some questions. Maybe changing 8 to 3 will not work, maybe. The thing is that if 8 will be changed to 3 here, then we will cover that in the first part of a solution. We said that first we consider all the adjacent pairs where one value is 2 times bigger than the adjacent value. So here 3 instead of 8 here would be 2 times smaller than 7. So for neighbors we would already decide to take some other values. Okay. We'll start implementation. Maybe I will take a look how much my face covers. Well, I don't have to run YouTube for that. I do have to. I just want to know how much to the right I can implement. Maybe I should open a black screen in my top right corner to cover everything. Okay, up to not. Maybe I should open... okay. Let's read the input, of course. No, we just read... we read n and we read the values of cases. Let's call this array A. I don't see why not. And let's start doing something. First, we want to check for adjacent values where one value is 2 times bigger than the other one. Also, we should... a question from this happens, is it possible that values will be negative? Because then -5 is not really better than -2, or something like that, or -3 is not better than -2, even though it's bigger than 2 times -2. But here we have that values are positive, not even 0, what also could be a problem maybe if we compare 0 with 2 times 0. I'm not yet sure how to what to do exactly, but generally we want to do if ai is bigger than 2 times ai plus 1. One question is whether the question is whether it should be bigger or bigger and equal. And all the time when you put some inequality in your code, you should think at least for a second whether you should write or equal here. In this code, I think it will not hurt us to write greater than or equal. The thing is that if we get, for example, 16 and next to it 8, we can say that the guy between those values will take 16. It's okay. He will not want to switch to 8. He's indifferent between the two choices. So I think it's okay to write greater than or equal, and I think it would also be fine to write greater than. Okay, we've read the input. The output will be... what will be the output? The ith number is the index of cake chosen by the ith person. Okay, so let's create a vector, like an array for answers, filled with -1s. So it's something like array of n filled with -1. Okay. At the end, we will print that. With coutts. Well. And here you can see that I print a space after every number. The thing is that theoretically we shouldn't do that because the output is n numbers with spaces between them, but almost all the modern platforms, judges, things like that, ignore that last space. The thing is that I would print, for example, instead of 1, 2, 3, I also print this space here. but as I said, it isn't an issue in modern judges. So I don't have to write some special if for that. One more thing is that it's better to add 1 here if up to this moment I want to use indices from 0 to n-1. You should set your face to bottom right corner. But sometimes maybe I should. I don't know if it will be stranger for you, because I think my face looks in my bottom right, because this is where my keyboard and monitor are. So now I look at the bottom of a screen instead of looking in direction of code, but doesn't matter much. Okay. Tell me if my face now covers something important. Okay, what do we do here? If AI is greater than the next value, 2 times greater. Also, to not get out of boundary, here we should write modulo n to get +1 minus n. If this is a case, then what happens? It means that this cake is very valuable, and that next person should eat this cake because it's 2 times bigger. So we will write answer of something is equal to I. So that person eats the ith cake. I'm not sure what I should put here. It depends on, I think, numbering of cakes. So whether the first cake is after or before the first person. Let's see in the statement. In the input section, we assume that the ith person chooses between ith and I plus 1 cake. So person, we here choose between cakes I and I plus 1, so here it's about person number I. Okay, and similarly, if that next cake is 2 times bigger, that the person should eat that next cake. Makes sense? I think so. Also, I think many times we'll use a function I plus 1 modulo n. So let's create a function for that. Let's call it next. And here we return I plus 1 modulo n to just make our code nicer, easier to read. And while we made this improvement, again, I'm not sure then if it makes sense in Polish Olympiad if we count CPU operations, but it will not hurt. Modulo operation is quite slow. If it's possible, you should avoid it. And here, if to a number between 0 and n-1 you add 1, you can implement this function without modulo, because you can write if I is equal to n-1, return 0, otherwise return I plus 1. Now this function is a bit faster, and a bit here means that it's like 5, maybe 10 times faster. And let's say that also we'll want a function previous, that if I is equal to 0 returns n-1, otherwise it returns I minus 1. There's one danger with these functions. What if, for example, we write next of n? It will not work correctly. So to be safe, let's add an assert just to check if we don't remember about that in our code. And if this assert fails, we will then try to correct this function or change the usage. Shouldn't it be if I is equal to n returns 0? So here I assume that the index I got is between 0 and n minus 1, so it can't be n. And maybe what you mean is that if the increased by 1 value is n, because then we want to change to 0. But notice that I didn't increase I by 1 here. So I get number between 0 and n minus 1. For n minus 1, this is a special case, we go to 0. And for every other value, we go to I plus 1. By the way, if you aren't sure about things like that, just leave I plus 1 here. And later, if you get time limit exceeded, if you already know that your solution passes some tests, passes the example test, then it's better to improve like the running time. But I will leave this version. Okay, so I assigned something. Now what I must do is what I have to do. So for example, I have this situation. I assigned some values and I must care about the remaining values. So in some order, for every person I should choose left or right cake. Here, like on this drawing, it makes sense to start, for example, from this place, to just do some order from the place where we chose something, but we don't necessarily have even these two arrows. Maybe we didn't choose a single thing. So my idea is to every other person to choose the, let's say, a cake to the right, and then maybe switch some people. So here it's a moment where during a contest it's better to spend like a minute or two to think about implementation, not to right away dive into implementing and just think what will be better, to not write something and then realize it doesn't make sense, I should write something else. So let's think on this drawing what we would do. Let's say for every person we would take the right cake, a cake to the right. Okay, that's it. And then in some order we would consider changing if a cake in the other direction is better. Maybe one iteration of that is enough. But what if the drawing isn't that regular? Here we saw a situation where both people next to this big cake chose it, but maybe here instead of 6 we have, for example, 13, and then if I'm not mistaken, it isn't sure what this person should do. So also this scenario is possible. Right now we can't decide immediately about any person because no value is 2 times bigger than the adjacent one, except for this place where we decided the direction already. So let's now for every person choose a right cake, or maybe left one, assuming that cake is not taken. So here we saw a situation where this is the only taken cake at this moment. But also it would be possible that the drawing is symmetric to this one, like this. So let's stick to saying that later for every person we'll take a cake to the right. So right now we would get something like this. Okay, and now this person, like we say that, I'm not sure I'm saying correct, let's say that every person takes a cake in this direction. So this person can't take this cake, or maybe he should, because it's already taken, so it's like a bit smaller. And the question is it an issue for us? Maybe we can still do something like this for everybody. And the other thing is that let's not forget that we put some multiple rules. We found some multiple rules at the beginning. And is it enough to just apply the first rule? Or should we still do some iterations of the next rule as well? The next rules. And now it's a moment to think about that before implementing like the main logic. Just for your information, I also don't know what exactly should be done here. What we know for sure is if no value is 2 times bigger than the adjacent value, we can for every person assign a cake to his right. We know that. So the first rule covers a different scenario where we know that we should put some extra arrows, something we are already sure about. What now? Now, can we say that every other person will choose a unique cake? So, except for our choices made with this first rule, and so maybe if these values would be smaller, then this person would also take the same cake. Maybe after considering that, we can now say that every person chooses a unique cake. So a cake that only he would choose. I think a counter example for that would be, what if here there would be also a big value, for example 20 or 25, then this person chooses for sure this cake, and we have a strange situation for this person, because we can't say that now for every person we take a not taken cake, because this person must take something that is taken already. But maybe now for every person what we can do is to greedily choose a cake that is better. Let's see if there are some issues with that. So like this person would take this cake. What are possible issues? The thing is that it must be true for this person, because his neighbors already decided their choices. So now this person will either get 10 or 12 and a half. So he must get 12 and a half. For example, this person, assuming that none of his neighboring cakes will be taken ever, he indeed should take this cake. But what if later it turns out that there is some person to his right? Of course it isn't true here because that person already decided. But what if this person later sees that this value is better for him as well? So we should try to prove or somehow find a counterexample, whether it's possible or not. The thing is that if, let's focus only on this part of a drawing. So let's say that this, and this for a moment let's remove. This person at this moment takes 8 greedy. An issue happens if later 8 is also taken by a next person. So we have someone here. What if it turned out for him to be better to choose this? We said that right now no value is 2 times bigger than adjacent value. But this 8 already changed for him to 4 because somebody is already taking him. Somebody is already taking half of this cake at least. So apparently if we have like longer circle, here there was some other value that is not 2 times smaller or larger, for example 6. And the next person had to choose that apparently because we said that this person prefers 8. Otherwise, this person, like if this 6 is not taken, something that is not 2 times smaller, then for this person it's better to get a whole 6 instead of half of 8. So if this issue happens, then apparently this 6 was taken like this. But then here there has to be also a value that is not 2 times smaller or larger, and the same logic happens. Apparently this guy for some reason took a 7, and so on, until eventually we encounter a cake that we already decided about, what is possible only if some value was 2 times bigger than the adjacent value. So maybe here it was 12. So if here it was 12, then this scenario is impossible because this person would take 10, even if it's only half of that. So the other possibility is that it's 2 times smaller than 7. So here, yeah, indeed, this 7 had to be taken. And then this 6 had to be taken, then this 8 had to be taken. So now it's possible. But this is a scenario coming from that first phase, with some value being 2 times larger than the adjacent value. So maybe instead of doing things greedily from some place, it will be correct to do things greedily starting from some person next to a taken cake. So here we know that 7 is taken by this guy, half of 7. Now the next person chooses 6 and so on. So maybe here every person will take cake in this direction. The issue will be if eventually we will encounter also a decided situation. So it would have to be, I think, symmetrical to that. So let's say that here there is a guy who we are sure takes this 7. So this 7 is taken in half. It's of course possible when here there is a small value, like a 2. Then let's think what to do with this whole segment. Whether maybe the answer will be no in this scenario, I don't know. So here there are 2 cakes, 2 not taken cakes, and 3 guys. And I think that here this solution seems valid. So right now this guy shouldn't change a decision because each of adjacent cakes is already taken by some neighbor, so he takes a bigger value. Okay, this guy has the same situation. Both neighbors are taken, both cakes are taken, so he chooses bigger value. And for this guy, he chooses a cake that is not taken, so he gets a whole 6, while otherwise he would get 3.5. So this scenario is valid. So what happened here? Okay, a new idea for lemma, at least in this interval, this special interval, no cake will remain not taken. So this is maybe not very useful lemma. Not cake will be taken in the special interval. And the special interval means here this part. So an interval between a cake taken by someone for sure and a cake taken by someone for sure. So here the special interval having 3 people and only 2 cakes. It will always be one more person than the number of cakes. And the lemma seems easy to prove, because if in this interval no value is 2 times bigger than adjacent value, so if a cake is not taken, where it could be not taken? Well, if there is a 6 between 2 7s, then it's possible that this guy takes, so this is one person, he takes something to the left, a 7, this is like one person, this is some other person and he takes 7 to the right. So here a 6 would be not taken, indeed. But that assumes that here the next person also chooses a thing to the right. I don't know, maybe it would be an 8, maybe 6. The same here. So here there is some person. So also there's something here, some cake. Because otherwise, if this person took a 7, so then 7 would be decreased to 3.5 for the next person, then this person would take a 6. So like from this moment outside, every person should take like more out cake, and eventually, let's remember that we are in this interval, eventually this person would have to take this cake. And is it okay? Is it possible? It looks possible. A bit strange, but possible. Because here, for example, we can say that, let's say that this like 3 7s denote exactly this like special case, things taken in the first phase already. So I think it's a perfectly valid scenario. I don't see an issue with that. So there could be cake that is not taken at all. What surprised me, I thought that the lemma would be correct, but well, it's important to try to prove it, because like we now see that it's possible to be not true, but it's because we tried to prove it. We tried to consider some cake that is not taken at all, and it implied some other things. so it wasn't a good lemma. It wasn't a good idea. I more and more lean towards trying the improving greedily approach. So choosing something and then trying to improve that, fix that. But I don't see why it would work efficiently. By the way, is it true that if we break the circle into chains, such that the ends already have a fixed answer, we have a solution such that some prefix of this is eating right cake and suffix there left? Yeah, an idea like that could be true, but like, I also thought that in this part, maybe, like this drawing shows a scenario where some first number of people take a cake to right and then to left, but I think what I printed here when considering this lemma showed a different possibility where some interval of people took a thing to their left and then some interval of people to their right. Maybe it's true that there will be like only two intervals here. So maybe it's true that here it's possible to split people into two sub-intervals such that in every interval everybody, like in one interval, everybody takes a cake in the same direction. This is a very good idea. I don't know if it's correct. One thing that also I want to tell you, but we will not do that here, is that if you consider multiple ideas like that, one possible, of course, you can just implement something and submit your solution, but if you see a wrong answer, then you don't know if you made a mistake in your implementation or the idea is wrong, so I don't recommend that. The other way to deal with that is what we do now, so try to guess some lemma and prove it, or find a counter test, and in this process you also understand a lot more in the problem. And the third possibility is to write a brute force, I don't know, exponential one. Here it's easy to write 2 power n brute force. For example, with brute force we could confirm that there always is a solution. Also in this brute force, for example, we could check if our rules here are correct. So if brute force finds a solution, then to brute force we can add these rules to the beginning, and if we force that, do we still find a solution? If yes, and if it's confirmed on thousands of tests, then yeah, we don't have to prove anymore the observations. Similarly, a lemma like this could be just checked with brute force instead of drawing something and trying to prove yourself. So it's sometimes a better way. The disadvantage is that if it doesn't work, still, like, there's that issue, the same issue as with submitting. You aren't sure if you made a mistake in the program or the idea is wrong. But it allows checking. If you have multiple ideas, then it allows checking them faster. But if you have time, maybe better, more certain, sure way is to try to prove stuff. Also, it teaches you to prove things, what is important and useful in problem solving. Okay, so this lemma was not true. Our, one possible new lemma is that this interval could be split into two, where every interval is only one direction. Do you usually analyze problems by writing the observations, thinking process, outcomes on paper, as you're doing to explain for us, or just scribble some main things and rest thing is done in mind? I wonder if I'm trying to find some paper, maybe from a contest, to show you. Of course, I must be careful with that, because sometimes I invent problems for competitions, and I don't want to show you, I don't want to spoil my problem from a future contest. Okay, so for example, let's see if it's visible. I hope it's visible, more or less. Well, for a moment I can make this screen much bigger. These are my notes from last Topcoder round. These are my notes from last Topcoder round, and what you could see here is that I do some general, like, for sure formulas are good to be written on paper, also some drawings, but most of the thinking part can be done in mind. For example, I would maybe draw something like this. Of course, it's quicker to do it on paper than in Paint. But like the proving part is done in mind usually, unless you need formulas. Also, when I try to come up with a solution and I don't know, I have a sequence of numbers, for example, some, I don't know, 4 numbers from even the sample input, I would just write them down here, and looking at them, I would try to invent a solution, to think about properties, observations, maybe we should here split something, things like this. So a big part is looking at a picture, a drawing, and trying to understand something there. Okay. So here it would be good to solve this problem already. Also, of course, talking about things and explaining takes more time. So here, I think in this problem I would follow the same pattern in this problem about Gluttons. Just it would be faster if I didn't have to talk about everything, because like mind works faster and doesn't have to explain things exactly with words. Just like maybe I would draw more examples to see if some lemmas are correct or not. I don't know exactly. Okay, so let's maybe now take a risk, and let's try with that approach that for every other person chooses a thing to write, and then in some order let's try to improve it. If somebody should change a direction, let's do it. I think that if, for example, the lemma about splitting this interval into 2 is correct, then this approach will work. Maybe also this lemma is not correct, but still this approach would work for a different reason. So right now my idea is to write that down to see if it passes the sample test. Then I think we can generate some random inputs to see if it always finds a solution. If yes, then awesome. If not, we will have an exact test for which we should analyze how to do it, or maybe it can't be done. If it's a like hard to analyze test, then maybe it's a good idea to write a brute force, then just 2 power n brute force that checks all the possibilities, and then we will find whether the answer for that test is no. So I will do that. Actually, I think if we do that, we don't have to implement this special part for 2 times bigger than the neighbor. because it will be done automatically. So I will comment that, and instead, for a moment, for every person, let's choose this cake. And now we try to improve stuff. So let's say that checking guys in the same order. I don't know what order I should choose. Let's think later. Consider changing e to I plus 1. So what do? We want to know whether a cake is taken by the other guy. So let's create a function that, let's say, finds value of a cake. So we said that I think person I can take cake I or I plus 1. So cake I can be eaten by person I or I minus 1. So here, if maybe this. So count will count people that are trying to take this cake. So return answer of I is equal to I. This means person I eats this cake, plus answer of previous person is equal to I. Like this expression in C++ works correctly. It will return 0, 1 or 2. So this value will be 0 or 1, and the same for this value. Of course, you can write here if answer of I is equal to I something plus plus plus, and the same for the other thing, but it's an easier way to write it. Okay, so here, for a moment, let's change answer of I to minus 1. Now, the value of taking something will be either the whole value or half times that. So here, let's create the other function that would return the value of the ith cake, and it will be if count of I, so if it's already taken, return value divided by 2, else, let's say assert count of I is 0, return value. So here we guaranteed that that cake we will consider taking isn't right now taken by either person, by this person. So it can be taken by at most one person. So this is why here I only consider that the count is 1 or 0. It's impossible that it's 2. This is why I put an assert here. And if it's already taken by the other neighbor, for me the value is value divided by 2, and otherwise the whole value. A small issue here is that this rounds the answer. I don't want that. So to get integer values, instead of value and value divided by 2, let's just consider that same thing times 2. Equivalently, while reading the input here, I could multiply everything by 2. It doesn't affect the answer in any way, but it makes division by 2 like not getting into real numbers. But also I can do something like this. Okay, and here we are choosing between I and I plus 1. If value of I is smaller than value of next of I, then choose that next of I. This is something. Let's also say that Okay. Maybe we should do that 2 times. Maybe you should iterate 2 times over the circle. The thing I'm worried about is that maybe we start from some position, do it in some order, but we should do it a bit more. So I think it's better. Of course, I don't here prove anything. Let's call it repeat. So I want to repeat the same thing 2 times to make sure I do pass a circle starting from any point. Of course, it's done without proving anything, but just it's some intuition that came from trying to prove a few lemmas and to see maybe this is correct, and if this lemma was correct, I would now get a correct solution. Also, I'm not sure about the order. Maybe I should go from from n to 0. So maybe I will change it here later, or maybe I should here repeat the same thing but in the other direction. I'm not sure. Let's try that on the sample input. Here I don't have a variable value. I should use AI. I don't have input, so let's copy that from the statement. Maybe record one contest and post it on YouTube, maybe later, but I'm not that strong of a participant. There are stronger people like Petr, and he does streams, so I think it's better to watch him, and I will stick to my more educational content with explanation. Inputs with only 7s, I can, of course, maybe let's call it input 2. I can create that, but I think it's quite easy input to solve. But we can see if the program makes sense. Okay, for the input with only 7s, we get that every person takes 1 cake, like to his left or right, I don't know, but it's for sure okay. For the sample input, we got something different than what is described in the statement. So let's see if it's correct. What do we have? 5, 3, 7. Five, 3, 7. By the way, I already today tried to check in the internet whether some graphic tablets work with Ubuntu, and I'm planning to buy some Wacom tablet to do drawings with hand instead of this paint thing, because it would be much easier to draw there. Okay, and here let's see how it's numbered. So this was the first cake, second one. So this is first cake, this is second one, and this is the first person, because first person can choose between first and second cake. And let's see what my program does. 1, 3, 3, 5, 5. 1. The next person chooses this, and 5, 5. Is it correct? I think it isn't, because the first person should choose. No, it's okay. So this person gets value 5, and changing direction he would get 3. This person gets 3.5, that is bigger than the other possibility. The same here. and these two get 4.5 instead of respectively 2 and 2.5 here. So it works correctly. I would submit that at this moment. A nice drawing pad will be cool, maybe get an extra screen as well for browsing and chat stuff. Maybe. I think that chat should be put as a window that is all the time seen. Also for people that, I don't know, watch full screen or watch it later. Oh, I didn't choose a language. Well, I have also my laptop here, so if I want to do something that you shouldn't see, I can use it for that. The disadvantage is that I can't then move. For example, I find here some link, I can't simply move it here. But the other thing is that on this computer, I would prefer not to be logged in Facebook, Gmail. I also don't want to have multiple files. For example, like this is freshly installed Ubuntu, and here there are not really many of my files or directories, because I don't want to by mistake show something confidential. Okay, so here we got quite a few wrong answers, and of course we are a bit lucky that we are shown this this thing. On contest I would just get wrong answer. Let's try to kind of desperately change this to 3 repetitions and also try a different direction, but then the next step will be to do something smart. So what I will do is try to find a counter test on my computer with random tests. So regarding the previous topic, yeah, a second screen wouldn't hurt, but I'm quite okay with my laptop sitting next to me. It isn't that bad. Also, my table that I have is quite small, so I can have many things here. And we got 100 points, hooray! So apparently either tests are weak, or after this change it's then okay. So we consider both directions. I think, my guess is that 2 repetitions would be enough already. Let's see. At least to pass tests. I also wonder whether this is indeed a correct solution. So later today I will check it for random tests. Like with millions of random tests, we can be more sure. Yeah, and we got 100 points, so 2 repetitions was enough. I think the important thing was to also try the other order, or maybe only that other order was enough. Let's see. And let's try also with 3 repetitions. And also I will read the editorial that is available in Polish to see what is the intended solution. But my guess is that the intended solution just analyzes many possible cases, and then, well, maybe it does that. So considering only one direction isn't enough. You have to go both ways. Why can it make sense? Well, maybe because in our analysis, often we said that when some guy for sure will choose one direction, then maybe depending on this direction, the interval next to him, like interval of values where no value is 2 times bigger than the adjacent value, depending on this, maybe we should go either in this direction or maybe in that direction. So maybe it's about that. By the way, YouTube and Twitch chat stays with the stream. Okay, that's cool. I didn't know about that. Yeah, that laptop hack is nice. And also I can have, I don't know, Facebook open there without worrying that I will show something, or I don't know, Gmail. And also I have all the files, my private files there, including problems that are meant for future competitions. Okay, that will be about the second problem. We have 3 problems to go, and the problem just like our Gluttons problem took a lot of time, but this was because of explaining a lot of things and also trying different lemmas, approaches. And now we see that I said very early that I have an idea that maybe we should greedily try to improve things. And on a contest, depending on, for example, penalties for wrong submissions and whether you have full feedback or not, it's sometimes a hard decision, a hard choice. Should we risk and implement a solution we aren't sure about? Like, with time, with experience, you will have better and better intuition to know, to like estimate how likely you are to solve a problem correctly with this approach. For example, in ACM IECPC contest, there is only one computer for 3 people, so I would spend more time with paper, trying to prove that, trying to see if it's okay, if I see counter tests, while on individual contests where you have access to computer, maybe it makes more sense to just implement and submit, or to write a brute force, because you have computer, you can use it. So it's sometimes hard to decide about it. The next problem is squares. I will read that, and again, you can find that by link in the description. So the composition of a number is writing it as a sum of different squares of numbers. For example, 1 plus 9 plus 16. They have to be different. And we will try to represent a number as a sum of different squares, such that the biggest of them is as small as possible. For example, a number 30, let's create a new directory. For example, number 30 can be written as 1 plus 4 plus 9 plus 16, and also as 1 plus 4 plus 25, then it's better to choose the first representation because the biggest number is smaller. So k of some number is that largest value. So here k of 30 will be 16. Well, it's the square root, so it's 4. And we also are given the definition of overgrown numbers. And it's number is overgrown if its k value is quite big, and we say x is overgrown if there is some bigger number, bigger or smaller? Yeah, bigger, that has smaller value of k. So for example, if k of 30 is 4 and k of 40 would be 2, for example, it isn't true, but if, then 30 is overgrown. And for number n up to 10 power 18, we are asked about k of n and about the number of overgrown numbers smaller than that. So in some interval, up to some place, we are asked about the number of overgrown numbers. I think it might be easier to approach it from the side of counting not overgrown numbers. So a number isn't overgrown if there are no bigger integers with smaller k. So let's write that. X is not overgrown if and only if all y values bigger than a satisfy k of y is at least k of x. And since we will know okay. So if there are values k for every next number, okay, we are asked about such places, such values, such that everything to the right is great. Okay, like sometimes it's good to spend a moment to understand something more intuitively, like not to have a complicated definitions. Do you have some questions about the statement? Thanks a lot for streaming. Thank you for watching. That's all. And the statement says that the value of k is infinity if it's impossible to represent the number as a sum of different squares. So it's hard to say anything about that overgrown part without first trying to understand something about the k value. So questions that might appear are: do many numbers have infinity as the number k? So maybe starting from some point, all the numbers can be represented as the sum of different squares, or maybe not. Also, how big those values can be. Maybe this will be in the complexity. For example, it makes sense if the answer is of magnitude 10 power 6, maybe it will be in the complexity. And why? Because, or maybe not, if you write 1 plus the sum of squares up to n squared is something of magnitude n power 3, n cubic. But the easy explanation for that is that we have n values and their magnitude is n squared. So it's n times n squared. Also, this exact equation is equal to something. I think it's something like n times 2n minus 1 times, I don't know, n minus 1 divided by 6. I don't guarantee that it's exactly that, but there is a formula for exactly this equation. It doesn't matter. So, of course, maybe we don't have consecutive values here, but if the gaps between values aren't big, then maybe the answer, so that maybe let's not call it n, let's call it k, because it's that biggest square. So maybe then k will be of magnitude n, the value from input, like cubic root of that, because this is of order around of k3, and we want it to be equal to n. So from this we get that k is n power 1 divided by 3. I'm not sure about that. Also, maybe it will be much harder because of infinities. So the question is, how many numbers are representable in this way? In this problem, I think it's a good approach to write some program and see what it shows us. Once again, I copied the 2 lines to make reading faster and printing. Let's say that we read n, but we will print everything, all the answers up to n, just to see a lot of things. So a function solve gets some value, and let's say that it just solves a problem for this value. Let's say solving a problem will mean just find k of n for starters. And also in the statement we are given a few values of k, and we will be able to check if that's if our solution, our slow solution, matches these values. Melisenu Victor said it's n times n plus 1 times 2n plus 1 divided by 6. Okay, thanks. I was close. I just had to put pluses instead of minuses. Okay, so we can write a recursive solution that tries everything possible, but it makes more sense and it will be faster to make it like knapsack, to make DP. So maybe we'll do that here. So it's kind of a knapsack where you can take a value 1, 4, 9, 16, and so on. And for every number that we can get as the sum, we ask at what moment it was achievable. Okay. So let's fill first the answers with infinity, I think. It's always good to create a constant if something is indeed a constant. And answer of 0 will be 0. And now we iterate over squares. And writing it knapsack here in this direction would be wrong. So here we already, let's say that it's the sum already. If we already have a sum s, then sum s plus x squared can be something like this. We'll figure that out in a moment. Okay, but this will be wrong. I will talk about that in a moment. Here what I wanted to write is that if answer of s plus x times x is infinity still, then answer of that is x. And here instead of, we don't need that function, instead we just print all the things we found. Okay, why this loop is incorrect? Because it allows taking one square multiple times. Like for x equal to 1, here first we have s equal to 0, so from 0 we will move to 1 in dynamic programming, so we allow some 1, but then from 1 we will move to 2, and so on. So here I would just write it in the other direction, what you often do in knapsack. So this is decreasing value of s. And it's wrong, so maybe I didn't do it correctly. Okay, why is that? Because here I don't use answer of s, so this should work. Okay, we have some infinities, we have some answers. Let's check that for 8, the statement says, for 8 we have infinity. Indeed we have. For 30 we have 4. Indeed we have. For 378 we have something. 378 we have 12, and for 380 we have 10. Yeah, it matches. So here what we can do is to see if for somebody it's the first stream, I will repeat that I have 2 buttons for compilation. One is F9, and you can see it here. I must sign into chat to be able to use it. I don't know why I'm logged out. Can you mute that Ubuntu sound? You will not hear it anymore, I think. Here we go. So this is my flag for compiling with like debugger flags, but it's slow. And also I have a button to compile with O2 optimizations and without those sanitizers to then do something faster. We still hear that. Okay. Let's try now. I think now you shouldn't hear it. I will compile a few times. And also there is a delay, so I must wait a little bit to... If I ask about something, then I get the answer after like 10 seconds, unfortunately. So is it okay now? Okay, nice, thank you. So let's run it for some big value. And for big value, we see something interesting, because many values are the same. So we have 67 for a long time. For a very long time. Let's print that in a bit better format. Let's say if answer of I is equal to the previous answer, cout dots, while that is true, increase index by 1. Now we get something that is easier to read. Let's run for 1000. So here we get like, this means an interval in which we have a lot of tens. and we see that for some time there are two values k that are like alternating, 10 and 11 here. Then it switches to alternating between 12 and 11, then 13 and 12, and so on. What we get for 1 million? Okay. So we were right that the biggest possible answer is quite small. So for n equal to 1 million, we have this value equal to around 100. So likely for n equal to 10 power 18 from the input, this will be 1 million. So it's okay to have that in complexity. I also wonder how long can we get infinities, but apparently after some time, I think that 128 is the biggest value for which the answer is impossible, so for which k is infinity. Okay. So, what now? What ideas do I have? Some idea is that while n is big, maybe we should greedily choose some big squares to subtract from n. For example, maybe if, I don't know, if n is 1000, then we know maybe we can check that to get 1000 with some small squares, we would need to add 1, 4, 9, 16, and so on. But wait, we can use Python for that. 4, 9, and so on. A few more. Of 14. I don't remember how much it is. Okay. So we can see that we at least must add numbers from 1 to 13 square. And let's think about this example. For sure, it isn't enough to use those numbers, those squares. So we would have to replace one of these values with something bigger. Let's also, by the way, see what is the answer for 1000. Maybe I have that above. I don't have here. For 1000 it's 15. So apparently when we add here 15 square, but of course maybe remove some of smaller numbers, we will get like a sum exactly equal to n, equal to 1000. In this case, I think it's possible to remove, or maybe it's not that easy. But anyway, just checking how many numbers we should use at least. So it was 13 in this case. Well, we need something more, so we must at least use 14 square. So the answer is at least 14. And here we see that the real answer is exactly 15. And if, do you see here? Yes, you should. So here you see that the answer around 1000 fluctuates between 14 and 15, and maybe it happens like this up to 819, where 14 is enough. Let's see. Maybe I made some typo, because for 18, okay, it's okay. So here for 800 and 819 is the last number where 13 is possible, and for smaller numbers the answer is either 13 or 13 plus 1. Maybe infinity is possible for a larger value as well that we can see, like 2 power 15. Well, it's very unlikely. If you examine some properties of numbers, and it happens for a few small numbers, let's say up to 100, and then you examine numbers up to 1 million, and there is no number with this property anymore, and like the condition was kind of natural, you shouldn't think that somebody was malicious to you. It's a kind of, let's say, natural problem, like math problem, something almost coming from nature. Then you should expect that it doesn't happen for big numbers. It is possible, but unlikely. And binary search, I don't see what we would find here with binary search, how to apply it, because what we have to check is whether it's possible to get some number exactly. For example, can we get answer 14 for number 1000? I don't know how to do that right now, and binary search will not help. But if it's true that we can, like with this method, find roughly the answer, and then we know that the answer is that or that plus 1, it is some way to solve the problem. Okay, so here we see that what we see. Okay, so let's say that we are interval with n bigger than the 819, and that n is smaller than the next value, that is this one, so 1050. So we see that in this interval, starting from this place up to 1015, so up to here, the answer is indeed 14 or 15. So it's enough to check if the answer is 14, and if not, then it must be 15. How to check if the answer is 14 here? Well, we have this expression, and the answer is 14 only if we can remove some subset of that in order to get exactly n. So for example, if n is 1000, then the question here is, can we choose some subset of squares to get 15? Because then we remove that and we have answer 14. Okay. So in this case, here for numbers between 800 and 1000, we ask basically, can we get 1015 minus n as a subset of squares? If yes, then the answer is 14. otherwise else it's 15. And that value 1000 minus n is up to 200. Maybe this value will be quite small. Well, the difference between 1000 and 800, because from what this was taken, is exactly 14 square. So for the whole problem where n is up to 10 power 18, so the answer is up to 1 million, that difference between consecutive sums, as we computed here, will be, unfortunately, up to 1 million square. So for a moment I thought that maybe we can do some knapsack, some DP, with that as dimension, but here we see that it's impossible. Also, I can say that I don't have or see a proof that the answer in this interval is 14 or 15. But if we, this is why we wrote a brute force, to see some pattern. Of course, to be more sure, I can run it up to 1 million and check in code with some asserts, like if e is greater than some sum, then assert something, that the answer is this or this plus 1. But I believe that just by looking at this thing. Also, it looks like a good way towards the solution. Can I share my code library? My code library doesn't contain only my codes, but also my teammates from ACM, ICPC. So I think I shouldn't. You are free to go through my codes from competitions, like the visible codes, for example, from Code Forces. So, for example, I don't know, if you find some flow problem in Code Forces, you can find my solution and there will be my flow. But I prefer not to share everything because it is not only mine. Also, you will learn a lot if you implement it yourself, for example, FFT. Also, there's only 115. Every interval of 15 is of length 1. I think it's not true. I think I saw some, here, you can see 991, 992, and 993 all have 15s. So it isn't true that the intervals are ones. This is answer to Meliscano Victor, that 15s are single. But yeah, observations are like that are useful, so we should try to see something like this. The bad thing about problems like this are that sometimes they require some crazy observation, and generally I don't enjoy just looking at numbers like this and seeing patterns, because there is not much algorithms in this. Of course, maybe a good approach here is to sit with a piece of paper and try to understand some things, try to understand why it's this or this plus 1, and maybe from this there is a solution. Okay, a new idea is that we ask if what we ask here we figured out that we need to find out whether there is a subset of those squares summing up to some number. But we also saw some time ago that infinities here appear only up to some moment, and then apparently there are no more infinities. So starting from some number like 129, all the numbers are possible to get as a sum of squares. So maybe let's here, instead of just like numbers around 1000, let's run it for like, I don't know, 100,000. And what we expect here to see. Let's see where numbers 66 and 67 start to appear. It's like here. So around value 93,000. And the previous pair of values happens between 8, 9 something. Okay, so where 66 appear for the first time, it's 93,000 something, 93,500, something like that. Then what I say is that if we add to this number 128, so let's see if we are correct here. So adding to this 128, we will get around 9366, and the observation is that starting from this moment, all the time we are possible to get that thing plus 1. So in this here we have 66 instead of 65, because in this formulation of what we want to check, this value that we want to get as sum of squares becomes greater than 128. And we noticed much time ago that starting from this value everything is possible to get. So starting from every sum, like 1 plus 4 plus 9 and so on, like we had like 800 and then 1000, then we have, this is I guess also some sum of numbers, sum of squares, consecutive squares. We only check the next 128 numbers, and starting from this moment everything else up to the next sum will be equal. This is my lemma. And let's try to check that with program. Radoslav Dimitrov, we can't get 1015 minus n only for a small number of values, so for larger values in the alternating interval we will mostly have the smaller alternating integer, 14 in this case. I would say the larger of alternating integers. Like here we are alternating between 65 and 66, and starting from this moment for a long time, like 50,000, no, 5,000, we have 66 instead of 67. But well, I think it's the beginning of a new interval of alternating value, so so here everything bigger than 128 is possible to get. So if 1015 minus n is bigger than this, then 14. So if n is smaller than or equal to 1015 minus 128, then it's 14. And if n is bigger than that, then it's 50. So you are right that only for the last 128 values we should check something, and then the answer could be the bigger one. Okay, and we also will need a fact about answer being only up to 1 million. So I think in up to 1 million places we'll check 128 values, and maybe it would be too much to have complexity 1 million times 120, but in each of those places the pattern will be the same, because the pattern depends on the first 100 values, where are infinities and where are possible numbers to get. So everything we will need for a problem likely will be the same. So we will just multiply something by the number of the same intervals to consider. Okay. So since the stream is quite long, I prefer not to implement that. I think we got to the solution, and I think it will be correct. So once again, the solution is to, here we already could compute everything for up to 1 million, for example. But the main thing is what we computed up to 128. So up to this times 5 to be sure. Let's compute something brutally with dynamic programming. Then the answer will be up to 1 million, we assume. In each interval like that, between two consecutive sums, sums of first squares, like we said here, the last 128 values could be bigger than by 1. Then there we follow the pattern from first 128 values, where are infinities and where are possible numbers. And other than that, we have a big interval of 14s. So for the complexity will be cubic root of n, because the answer will be in the complexity, that 1 million. And also it should be possible to, with those observations, to count the number of overgrown numbers. Do you see any questions here about that, or someone has any doubts about this solution? And if not, we'll move to the last two problems. And for those I already know solutions. I checked them in advance. And I think one we will implement, and one I will only show the main part. Okay, and now we will move to a problem Kinoman, in English Moviegoer. And here I will, maybe it's a good idea to give you a moment to get familiar with a statement if you want. And after that I will anyway say what it's about. And also, while we wait, I can answer some new questions if you have. Sorry, I'm back. Okay. The problem is quite simple to be stated. We are given a sequence of number. Let's say, I think we can say that every number is also between 1 and n, the size of a sequence. And we should choose some interval. And in that interval, we only care about numbers that appear as exactly ones. Because it's a sequence of movies, and you choose some intervals of movies to watch, but you don't like watching movies twice. So if you watch the same movie more than once, then you dislike this movie. And so for only numbers that appear exactly once, not more than that, you add them towards the score, and the question is, what is the maximum possible score to get? The score being the sum of values that appear a single time. For example, like you will not necessarily choose the whole sequence, because then many numbers could repeat, and those you don't count towards the answer. So we should just take some interval. And as I've mentioned, I already know a solution, but if you're experienced with similar problems, you should easily see a solution, I guess. But let's get to that. And there are two possible approaches. If you watched my, I think, first stream, I then said that if the input contains some intervals, like pairs of points, maybe it's a good idea to try to visualize that as points. And here we are not given pairs of numbers in the input, but still it's about some intervals. And how to do it? For example, let's focus on one movie. Let's say that it appears as number at index 3, 5, and 10. Then, if your chosen interval will contain exactly one of them, you get something towards the answer, towards the score. Let's say that one movie appears at positions 3, 5, and 10. Then, if your chosen interval is starts somewhere between 1 and 3 and ends between 3 and 4, then you get this movie towards the score. Also, if you get between 4 and 5, and the end of interval will be between 5 and 9, then the same, and the same if it contains 10. So this thing represents a case where your interval contains index 5, but doesn't contain other occurrences of this movie. So then, okay, and now it's possible to visualize that. And one possible approach to this problem is to try to draw it. Now, your chosen interval will become a point on the plane, where one coordinate means the beginning of interval, and the other coordinate is the end of interval. And the fact that something has beginning in some interval and end in some interval represents a rectangle. So basically, this means in some rectangle add plus, for example, 10 towards the score. This also is some rectangle, like 10 meaning the score of this movie, how much it increases the score of your interval. So the input represents some set of rectangles, there will be linearly many of them, by the way. Why linearly? Because for every movie you find indices where it appears, and it creates the number of rectangles equal to the number of indices, and the total number of indices of movies is n, because it's the whole sequence. So the number of rectangles will be also O of n, even exactly n, where n is the size of sequence. And now the question becomes quite standard. For a given rectangles on a plane, every rectangle, meaning points in this rectangle get plus something, find the best possible point. So point with the biggest score. And it's possible to be solved. Actually, I think we'll talk about solving this problem while talking about the different approach, because a different approach doesn't use planes and rectangles, but it will do the same thing. So let's just from this move to the second possible approach, the one that I would prefer more, I think, during a contest, but the implementation would be the same. So let's say that there is some input, I don't know, 1, 1, 2, 1. So I try to create an input for which also some movie appears at indices 3, 5, 10. So it's a movie number 2. It appears exactly at these indices. And what often should be done when you should choose some interval is that for every beginning of interval, maybe you should binary search the end, the optimal end, or ternary search, I don't know. It will not be a good case here, a good idea here, because for fixed beginning of interval, while you move the end of interval, the score will both decrease, increase. It can behave like that, because maybe you will find a new movie, completely new movie that increases your score, but just right after that some movie appears for the next time, so the score decreases. While you can binary search or ternary search only some regular shapes. For example, if the answer increases the whole time, or increases and decreases, then you can try to find in logarithmic time that optimal place, but for sure not if the answer can jump like this. Okay, but what can we do instead? Let's say that the beginning, let's first consider beginning being at index 1. Then we know that if the end will be somewhere here, so at positions 3 or 4, then we will see movie 2 exactly once, and we get something to the score. Similarly, if the end is at position 1 exactly, we can see we get movie 1 towards the score. If, for example, we have something like this, so there is an extra movie 3 here and here, and the beginning of our interval is here, then if the end will be somewhere around here, so indices between 4 and 6, the score will be increased by the score of movie 3. What is quite similar what we did previously with like rectangles, but here we have just, let's say, one dimension. So right now we do something like this. For every existing movie, there is some interval, and we know if end will be there, exactly there, we get plus something to the answer. So in a solution, in our implementation, we'll get queries, kind of queries. Maybe I will move code to the top more because it isn't relevant now. We'd get some operations like increase this interval by plus something, meaning if the end is there, the score is bigger by this. So first we initialize that like that. Like for every movie we find that interval of ends that is okay, so for which we would get plus something to a score. And then we ask about the best possible ending. So in the whole sequence, among all indices to the right, what is the best one? The one giving the best possible score. So basically we have queries: increase this interval by +5, for example, all elements here. Elements meaning value, so answer if we end here. Also increase this by something, and we ask what is the best possible ending, so the best possible number, biggest, in terms of score. And then we move the begin slightly to the right. We considered beginning at index 1, now we consider beginning at index 2. And when we move that begin, we have some constant number of updates to our structure. Because when we had some movie here at index 1, here it was movie number 1, then for that movie the interval of good ends, where we should end interval to get this movie exactly once, changes. So we should remove something. So when previously we said for this interval, if we end here we get plus something to score, now we put minus this value to score. And we move begin by one, and by one, each time doing constant number of updates, and each time asking what is the best possible end to the right. So there are two types of queries to our structure: increase value in interval AB by X, and find the biggest value in interval AB. This interval will always be from this moment up to the end. And this is possible to do with some, it's called, at least in Polish, interval tree, or like it must use lazy propagation, and you should know how to implement that. And I did that earlier today, or maybe yesterday. So I will talk a little bit about it. The issue with things like this is that maybe some people know this tree, maybe some people do not. I think generally a good way to learn it is to find some good tutorial for that. So I will quickly say about the idea for that. And by the way, also this is exactly how you would implement that version with rectangles, because the solution for that is to sort everything from the left, so to move with sweep line, and then when we move a sweep line and we encounter a new rectangle, when we start with rectangle, we increase this interval by plus something according to this rectangle value, and when we end we do minus this. So it's exactly the same thing. So okay, and here what I implemented wasn't the solution for this problem, and it was on purpose. Why? Because if you can, of course, you can write the solution for this problem and then put a tree there. But then it's harder to debug, it's harder to find mistakes. What I do personally, if there is some complicated or not solution, but it uses some structure, what you can also use is you can implement just a solution with this structure, not even solution to this problem, just implement something that uses this structure. So here I decided to just implement something that reads n, size of sequence, and q, the number of queries. And I read queries in form like I decided it to be plus, type of query plus means increase interval by something, and question mark means give maximum in this interval. So I just implemented that. I also implemented a straightforward brute force that just maintains an array of size n, and when there is a plus update, so increase everything in this interval by x, I just increase this interval by x. Similarly, I find the maximum. I also wrote a generator, a very simple generator that prints random n, random q, and just prints random queries of random types. And I stress tested that. So I ran that in bash, with bash for many tests to check that. And I recommend that to you during contests, unless you're close to the end of the contest and you don't have much time. You must risk and just not test and write a solution and hope that it will work. But especially for beginners, I recommend this way. So I did that. I made sure that my tree works with lazy propagation, and then I would apply it to a problem here, being now sure that it works. Okay, so a few words about a tree itself, about this tree, is that it's a segment tree where, of course, there's a root to children, next to children for every vertex, and so on. And when you increase something in interval, you don't want to move up to leaves and increase values everything by that value that you want to increase by only to increase in logarithmic number of vertices, like in any tree you would want to do. And then while doing that, you also can obtain, maintain the value of the biggest node, the biggest leaf in this subtree. And you also need value that I call lazy. It's for lazy propagation. About that you can read in the internet. And when we want to do some update, or we have a next query and we want to do recursively bottom, when, for example, first we increased all the values by 5, so only in root we put +5, but then in the next query we want to do something for smaller vertices below. When we are in the root, we should that 5, that is also stored in as lazy value, move to the children and then remove it here. So value lazy is something that you put to children and then change to 0 here. This way you know that eventually all the leaves will get that +5, but it will be done in logarithmic time. And the recursive function is something like you must store where you are in some vertex, you know ID of this vertex. So for root it would be 1, for children 2, 3, 4, 5, 6, 7, and so on. You also know interval of leaves that are in this subtree. You also know interval about query, because query was for some interval. And you also need value by which you add, and if it's a query for where we ask about maximum value, you also need maybe reference to answer to increase that. And you do a sequence of ifs, something like if this value of this subtree, sorry, interval in this subtree and interval from a query are disjoint, then return, do nothing. If the interval from query covers our subtree completely, then we don't go recursively below, just like with root, when I said, what if we increase all the values by +5? Then just increase value in root. And otherwise, we want to go recursively to children. So we put this lazy value, for example, if lazy value here is 5, we put place 5 to each of the two children. We change this lazy value to 0 to not do the same again later. Then we go recursively to children, and eventually we merge the result, like in all segment trees. And in this case, the function merge is very easy because it just, like in my code, big represents the biggest value in sub. So I just put, like in parent, the biggest value is maximum of biggest value in children. So it isn't a complicated solution. Finalizing tree or segment tree, code forces block entry 18,058. Maybe you can post a link here, or is it impossible to post links? What I use, I think, is a segment tree, and I don't know which source is good to learn from that. In the contest, do you implement seg trees or do you just copy from library? I implement them myself. Well, in my ACM team, Marek Sommer was better in that, so I would ask him. Okay, so I will post link. Okay, so Rishab suggests this block. I don't know if it's good, but well, I learned that many years ago. It was from Polish websites, so I can't recommend that. Why can't we use... okay, so if there's an interval, the question is, why can't we just increase value here by x and decrease here by x? I think. The answer is, okay, so if you do that, how to then answer about this smaller interval or something bigger like this? You only change some two values. And later, if you ask about some different interval, the whole idea of segment trees is that you will somehow know those changes while changing something if in two places just only, and then asking about other interval that contains that, you wouldn't know about that small changes. Okay. So yeah, so this is that, and here my suggestion is to just implement it, the whole, like the actual solution to this problem, as we iterate over the beginning of an interval, and we must know where the next occurrences of every value. And I strongly recommend for you, if this problem is not very easy for you, then try to find some time in the evening, or I don't know, on weekend, and try to implement that. One thing, implement this tree, maybe with tutorial, and like me, test it with brute force on random tests, and then try to use it in solution and try to get 100 points. While for experienced guys this problem is very standard, for beginners, if you didn't solve something similar in the past, you must solve this problem. And solve meaning implement. This is very important here. And we'll move to the last problem. Victor says, so we update two values, do partial sums. We must get logarithmic complexity. The thing is that we do, after every query, we should be able to answer what is the maximum value in some interval, or here maybe in the whole sequence. If you every time do partial sums that are linear in complexity, in total you will get n squared, because you have n updates and queries, and you do partial sums in linear complexity. So partial sums make sense only if you get one sequence, one thing, you do something there, and then you have questions about like maximum in interval, maybe sum of interval. Can we do a squared decomposition? Yes, usually when we could do a segment tree, we can also do a square root decomposition, but it will be slower. So it's better to do segment tree. Do we have here queries? Yes, we have. We talked about a solution and we boiled it down to queries: increase value in some interval and find the biggest value in interval. Remember that queries don't have to be in the input. Our solution showed us that we have some queries that we should handle. I explained that when I was talking about moving the beginning of interval, and then we said that when we move interval, for that movie that was at this previous place, for example, okay, we don't have example, the next occurrence like maybe changes, and we should update for which interval we say that if we end there, we have something plus to the value. What is the main difference between square root decomposition and segment tree? Square root decomposition is slightly easier. Sometimes square root decomposition is possible to be done, while segment tree is not, or is extremely hard. But square root decomposition complexity is usually number of queries, q times square root of n, while trees have complexity q times log of n. So it's faster. For q equal to, let's say q and n equal to 1 million, this should still work fast, like 1 second, and this will take a few seconds at least. So often with big values of q and n, organizers will require you to implement segment tree. So if possible, try to write that. Does it depend just on queries to choose one or the other? Usually you can usually both are possible. Just segment tree is slightly harder but faster. So, but if you see that values like constraints are up to 100,000, then you can write square root decomposition if you find it easier. Okay, so that was problem Moviegoer, and now the last problem will be wizards, sorcerers. Okay. And again, it's a problem, it's a quite hard problem, not easy for sure, that I solved already. I will give you a minute or two to read the problem for those who haven't. But generally for the future, I recommend for you, like I think it makes a lot of sense. For some streams, I will post in advance problems that we will be solving, and it will be much better for you if you try to solve them yourself first, to spend some time, because then when listening to me you will see what ideas of yours made sense, which didn't. You can also maybe ask more like questions that are better. Maybe why won't we do this? Whether this approach would work. And while just hearing a problem and seeing a solution or approach immediately is slightly like easier for you because you just follow my steps, but it will teach you a bit less. So I will be back in like 2 minutes and read the problem. One day before, do we have 8-hour classes? I will try to announce things with more time before. I first posted about these Olympiad problems like 4 days ago, but I understand that if it's posted a day before, it's harder to find some time, especially for a few hard problems. We'll be back in a minute. Okay, so the problem is we are given n people numbered 1 through n that we want to put around the table, and every two adjacent people, their indices, their numbers, should not differ by more than p, and p is very small, it's up to 3. So for sure it's an important number, and maybe for p equal to 1000 there will be no solution. And like, just to show you for what happens for p equal to 1 in that case. So every person should be, his neighbors should be different by at most 1. So if there is a person number 1, next to him there must be 2, next to 2 there must be 3, and so on, and then up to n, but 1 can't sit next to n. 1 can sit only next to one person, person number 2. So actually there is no solution. Solution is only for n equal to 1 or 2. So in problem like this you must be careful about corner cases. So for okay, this problem we can close. So also there is p equal to 0 case. So I think if n is equal to 1, then the answer is about the number of possible orderings modulo some big prime number. If n is equal to 1, then the answer will always be 1, because no matter p, there is one ordering. We can put that one person there. If p is equal to 1 and n is up to 2, then the answer is also 1, and otherwise, so p is equal to 1 and n is big, the answer is 0. For p equal to 2 we'll have some more complicated cases, but still something quite easy, and for p equal to 3 we'll have the main solution. That is quite hard. Girlfriend or wife? Girlfriend. Okay, so for p equal to 2, we can do some analysis. I will show you more or less how they should look like. So a previous problem was Gluttons. Okay, so I think a graphic tablet would be much better now. So we have a circle and we have a person number 1 somewhere, and we have, let's say, p equal to 2. What a beautiful drawing. Then his neighbors must be 3 and 2. There is no other way, assuming that n is big. Then next to person number 2, the only possible person is 4. Next to 3, 5. 4, 6. Because there is no other person, for example, at this moment. 4, because p is equal to 2, the only possible people are 2, 3, 5, 6. And the only not seated person is 6. So we do something like this. And it's the only possible ordering. If you read the statement, it also turns out that the order matters, whether after 1 there is 3 or after 1 there is 2. So the mirror of this thing is also a second solution. So for p equal to 2 and big N, we would get two possibilities. For p equal to 1 and n equal to 1, 2 or 3, maybe just like check yourself. It's some corner case. Maybe the answer isn't 2. And for p equal to 3, it's more complicated. There are more possibilities. But there's one more thing in the statement. We are given some like forbidden pairs. We are given k up to 100,000 forbidden pairs when there is one person and a person next to person right to him. So for example, it's something like after person number 3, the next person to the right can't be 4 or something like that. So here, in these previous cases, what we should do, after reading those forbidden pairs, forbidden directed edges, it's kind of a graph, we should check, for example, here where we had p equal to 2 and big N, we should check if ordered like this, so 1, 3, 5, 7, 8, 6, 4, 2, 1, is whether it's okay. So whether none of these edges are incorrect, like forbidden in the input. Anyway, we already, with this extra check in linear time, we can solve a problem for p up to 2. And only with p equal to 3 we have something more complicated. And I've read the editorial, or well, also the video tutorial by Milczek. I think you can later, well, we can do that now. I will, for Polish people or people, I don't know, maybe from Russia, I recommend this video. That is very cool and funny. Jan Milczek, he has talent to create funny tutorials. But the intended solution meant by organizers is quite, I would say, complicated. Maybe not, but it does a similar thing for p equal to 3, just with many more cases. And even that tutorial says you can write down all the cases and there is a finite number of them. For example, you can put 2 here and 4 here. Then there must be somewhere there must be 3, so maybe it will be here. And if it's here, then you get kind of like you already decided about the first some number of values, so you only have to now solve from 5 to n, something like that. But also maybe 3 will be here, then 5 must be here. Of course, here it's a case for p equal to 3. and so on. So there are a lot of cases. What I did, I think it wasn't intended, was some more generic solution, something that would work, but much slower, and it would be harder to do for a bit bigger P. And it's a solution with some masks, with some bit masks. What is that? So let's, instead of a circle, maybe we'll use that later. Also, we have now P equal to 3. Instead of a circle, let's imagine it in a bit different way, but equivalent. I already told you that I often okay, I maybe will print them like this. Often in problems you want to get something similar to other problems. For example, maybe putting things around a circle is a bit strange, it isn't related to any algorithm, but what we can do is we can say that if a person is to the right of some person, so a person to right, we just put an edge from one person to the next. For basically, then the problem becomes, for a given set of vertices, connect them into some big circle, like this, such that all the numbers will be on one circle, no edge will be forbidden in the input, and also every edge connects two numbers that are distinct by at most p. So here there couldn't be an edge from 2 to 6, but then can be from 2 to 5. So one possible ordering, I think, is like this, then 8, 7, 4, and 1. This is a valid order. Well, this doesn't look very nice. For p equal to 2, I think it's actually easier to make an analysis for this representation, because the possible solutions are either this order, so, and it was, by the way, equivalent to the one we printed on a circle when there was 1, 2, 3, 4, 5, and so on. So on one side it was 1, 3, 5, and so on. We have the same thing here. So we either have this in that direction, or that other second possibility was with this direction. When from 1 we first go to 2, then 4, 6, 8, 9, and then back by odd numbers. Okay, here we have a bit bigger p. And what can we do now? It's a thing that you would see after solving a few similar problems. Think that when we, maybe for example, let's say we go from 1 to 9, so we just count paths from 1 to 9, and also with that condition about p. So let's say that we can't do a jump, make a jump like this. So then usually this path will look something like this, maybe. Sorry for a terrible drawing, but it will try to go towards the right, with some exceptions. Generally, if we already, let's say, okay, let's say that we for the first time go to number 6 from something to the left, from the left. We for sure get there, we got there from number 3, 4, or 5, and it isn't true, but it's close to being true that we already for sure covered number 1 and 2. So let's say that those are visited already. Let's say, for example, that we visited 1, 2, 4, and 6. Then we must do something like this here. So from 6 we would have to go to 3. But my point is that if we get to 6, we almost can say that we covered everything up to this moment, and we only want to know which of numbers 3, 4, and 5 were visited already. So we say everything to the left was visited, some subset of numbers 3, 4, 5 was visited, at least one, by the way, if we got to 6 somehow. And so we would later have to visit the other numbers in this 3. So actually we can represent that as dynamic programming, or maybe something related to some strange Dijkstra thing with some masks. But, well, dynamic programming, I would say, where we know prefix that is for sure covered, already visited. And for the next 3 numbers, we know a mask. So there are 8 possibilities, because we have 3 vertices, 3 numbers, and each of them could be visited or not. So 2 power 3 possibilities. So this suggests a solution with complexity dp of n and dp of n8. Some questions now? No. Okay. Of course, if you have questions about what I'm talking about, ask. Do ask. Okay, and here the issue was that with p equal to 3, it's possible to do something more complicated, because we could do something, I think, like this: 1, 4, 7, then 5, 2, 3, 6, 8. So when we first get to 7, at this moment we only visited 1 and 4. And from 4 we get to 7, and it isn't true that everything to the right, to the left, sorry, was already covered, already visited. Why is that? Well, why is that is a wrong question. That it's just possible for p equal to 3. But here we should do something a bit more complicated, and now unfortunately it's impossible to explain that very well for people who are absolute beginners in things like this. But the solution is to, for when we go to 7 here, for things to the left from this line, to decide all the edges already. So here we know that there's an edge from 1 to 4. There's an edge from 4 to 7. And later, of course, we would have to visit 2 and 3 to somehow get back to 2 and 3 and to move back from them to the right. Assuming that we want to go from 1 to 9, just to simplify things a little bit. For 2 and 3, while we move from left to right, instead of just moving in order in which our cycle moves, or well, path, so 1, 4, 7, for every number in this order, we can decide from this number to what number we direct an edge, and to this number from what number an edge goes. So let's say that we want to somehow consider a scenario where we go in this way. So 1, 4, 7, 5, 2, and then to the right. So here, let's again print the numbers. Here what we will do is, for every next number in this order, we'll decide what will happen with that. So from 1, we consider that we go to 4, and now we don't consider what will happen with 4. Instead, we decide the fate of 2. So to get the same path as above, as here. For 2 we decide that from 2 we put an edge to 3, and to 2 we put an edge from 5. And for sure those edges can only be from and to the next 3 vertices, or from something to the left. So what I'm saying is that in the moment when we cover everything up to something and we say from every number there is an edge going out and edge going in, except for number 1, if we're just looking for a path from 1 to the last number, then we only have to remember in some mask the state of the next 3 numbers. So now we say that everything is decided about numbers to the left, and also we need a mask, this time a bit bigger, to know things about vertices to the right, 3 vertices to the right. So here we chose about some edge here, some edge going in here, maybe it goes from left to right, maybe the other way around. But now what we need for that is dp of n, and here mask. But what this mask should be? What I claim is that this mask should be this time 64, so 8 times 8, or also you can say 2 power 6, because for these next 3 numbers, for each of them you want to know whether you've already put an edge going in this vertex and whether you already chose an edge going out of this vertex. So we decided about all the edges touching, at least touching, like going in or out, vertices here. Some of those may be touched, some of these 3 vertices. For sure they didn't touch these 2 that are more to the right. So for each of these you remember a bit. Did I already decided about edge going into 5? And if I decided about an edge going out of 5, the same for 3 and 4. So you only need 6 bits. So mask representing an edge going in here, out here, the same for 4, the same for 5. 6 bits. So we get this, like this dynamic programming, and it's already possible to implement. I will show a solution that I've implemented earlier. And if you think about it, it turns out that it doesn't hurt that we say from 7 we must go back to 1. So basically we're looking for a cycle, starting from 1, visiting everything, and going back to 1. Okay? And the complexity of that is around n times 8 squared. Also, like, this is how many states you could have, but from every state, where we are, for example, at this moment, we want to move to the next number, so we want to consider things related to this 3, we must iterate over, like, if 3 isn't, like, the edge going out of 3 isn't decided already, we must iterate from 3 to which of the next 3 vertices to put an edge. So this is times 3 to complexity, and also we must decide about edge going in, times 3. So the complexity becomes n times very big constant. Fortunately, not all the masks here are possible to get, so it decreases the complexity a little bit. And why not all the masks? Because when we decided all the edges here to the left, then here I claim that among these 3 vertices, the number of edges going in and the number of edges going out must be equal. So among these 6 bits that represent edges in and out, there must be the same number of ones among bits representing edges in and edges out. And why is there the same number of edges in and out? Because on the left there was the same number of edges in and out, like 2 times the size of prefix is the number of edges that went in and went out. So, and every edge has exactly one begin, one end. So the number of edges going through this line to the left and to the right must be equal. So this, you don't need that in your code. It's just to help you analyze the complexity, because the complexity will be smaller automatically if you just iterate over this state, over the mask. And this is dynamic programming with the number of ways, where you store some number that represents the number of ways modulo 1,000,000,007. And just if that number of ways to get here is 0, then you don't progress forward. You don't count possibilities to move from here to the next states. So that thing about equal number of edges in and out is just for you to understand that it will not be that slow. But yeah, and it will be done automatically if you just put an if. If the number of ways here is 0, don't do anything here. One more thing, one more issue here. This is hard for me. Yes, I understand this is a hard problem. Just like for starters, you could try to analyze that for p equal to 2, where you can only move to the like neighbor or neighbor of neighbor. But yeah, it isn't an easy problem. Okay, so what else? There is only one issue with this solution. Of course, there is an issue that it might be too slow. When I implemented that, it was a bit too slow. I had to optimize it a bit, squeeze it a little bit. Also, like time limits were chosen a bit. In Polish Olympiad, at least years ago, time limit wasn't fixed for all the tests. So for some tests, time limit could be smaller. And I actually used this approach for all p, all values of p. And then it turned out that my solution is too slow for p equal to 1, because the time limit was like 0.1 second, and my solution took 1 second. So I had to go through those ifs instead. But like the main part for p equal to 3 isn't that crazy. Also, it might be helpful to see that when we go 1 by 1 to the right, so we increase that prefix by 1, most of the time, so we have 100,000 forbidden edges. So if, for example, in those 100,000 places there is something special, because of course when we put new edges we check if those are forbidden. And but in most places, all except that 100,000 places, everything happens the same. Everything happens the same when we increase prefix by 1, extend prefix by 1. So if, for example, once we moved from some mask here, we know that by adding this edge and this edge, we see that from mask equal to 3, we go to mask equal to 60, whatever. Then we can once do memoization, remember that those values, like what masks we increase, to then do the same thing for other places where nothing interesting happens, meaning there are no forbidden edges. So for those like 1 million minus 100,000 places, we will not consider all the possible edges going in and out. We'll just remember that we figured once out that from mask equal to 3 we can go to 60, from 10 to 15 and 20 and so on, just to improve the constant factor. But it isn't necessary usually in a problem like this. But there is actually one important issue about the correctness. The thing here is that what we do is we are trying to find the number of directed graphs where from every vertex there is an edge to some other vertex, and to every vertex exactly one edge goes in. But we don't consider the fact that there could be separate cycles, because also from the statement, from our solution, it comes that this directed graph we create must represent one big cycle. For example, it's not okay that for those numbers 1, 2, 3, 4, 5, we do something like from 1 to 4, from 4 to 1, and also from 2 to 3, from 3 to 5, from 5 to 2. Okay, so this is not valid, because it would represent sitting around two tables. So also we must add some special ifs. One is that if we add edge going in and out, for example, for vertex 4 we consider what we went from left, so for vertex 1 we consider what edge goes out, what edge goes in. So we must add an if and check that it can't be the same vertex. And if you do some analysis of this, you will also see one more possibility of a but not valid solution. It's also possible that you will get something like this. So here, if we have a cycle 1, 2, 4 and 3, 6, 5, we don't have any edge that goes from A to B and also from B to A that we forbid already, but we have something like this. And if you consider possible cases, it's the only bad one. So here also when we move with this considered prefix, what we should also do is forbid a situation where maybe it's better to cut here. So here we forbid a situation where we know that from left we only have edges from 3 and to 3. So only edge from one vertex to the left or to the right, depending on the implementation. Only from one vertex there is a waiting edge going out and waiting edge going in that we should decide later about it, because it means that everything else is already connected. And this new vertex starts a new cycle. And if we forbid that, we get a good solution. For those of you who are very experienced in competitive programming, I will say that for bigger value of p, this solution is also valid, but you must not to have those strange cases with forbidding stuff like this to avoid separate cycles. What you should also do is, apart from this mask, you should also store a state representing which parts of this graph so far are connected to each other. So for example here, for these 3 vertices, you would also store some small value representing from which vertices you can get to which ones. So kind of connected components. Maybe here strongly connected components, I'm not sure. So it would be possible to implement for p equal to 10. Just would be slower. And I will now talk about my implementation. Suggestion: along with this, also stream videos according to topics that would be very helpful for beginners like me, like DP. I will do that, for sure. I'm very new to all of this and I'm just trying to figure out what to do. And for example, on Sunday I did top-coder problems, and the main topic there was dynamic programming, but it wasn't easy. So those were very hard problems in dynamic programming. So I think I will try to see what ideas are good for streaming, and maybe, for example, every, I don't know, Sunday or something like that, there will be a stream for beginners with some chosen topics, like segment trees from zero. I'm not sure about it, and like this is my first stream, and every stream I'm trying something completely new and seeing just how it looks like. For example, Saturday was random code forces problems, Sunday was quite hard top-coder dynamic programming problems, and today it's problems from Polish Olympiad. You can also ask the question from chat that you want to solve. If you mean that I can ask chat about like suggested problem, it's okay if those are easy problems, but I guess it makes more sense to make it about one topic. For example, here I solve problems from Polish Olympiad from one day that I announced a few days ago in Code Forces. So people could first try to read problems, try to think about them. The other day I could, for example, solve geometry problems. But I think it's a bad idea to solve completely random problems from people. Also, if those are hard, then it will take me some time to solve. And then like a hard problem with me explaining things will take me like 2 hours to solve, and then it's almost the whole stream, so it isn't that good. So these are my thoughts. Like I welcome any like possible thoughts, ideas. Okay, and the remaining thing is seeing my code. So I had quite a few submissions yesterday, mainly because I thought with time limit exceeded for a long time. I don't know, let's see some random submissions. Those, you can see here that some tests have time limit like 6 seconds, and I solved that correctly, but some tests in the same group of tests has like 0.3, and likely it was something like p equal to 1, so then I had to add ifs for that, but then I added wrong ifs, so it took me some time to solve it. So this is my solution. So ignoring the cases about small n or small p, this is the main solution, and I will roughly go through that. So I create dp of size 64, just the thing that is here, and I go through vertices one by one. Like I didn't want to have memory n times 64, so I have just memory 64, and I like compute the next row of this dp. And so let's ignore update hack. It was that thing I said, like, to make it faster, that for all places except for 100,000 with forbidden edges, we can apply the same thing, so let's ignore that. But mainly, I iterate over mask from 0 to 64. Here you can see that if I see that the number of ways is 0, I do continue to make it a bit faster. And here is the main part. So let's talk about this, because this is the actual solution. So I have, like, I move one to the right, and I have one more new vertex for which I must decide about edges going in and out. So I iterate over to which to which vertex I want an edge, I would iterate over 3 values, like 0, 1, 2, representing like 3 next numbers, but I actually iterate to 3, so I consider 4 possibilities, and that value 3 means that I don't put any edge, because it's already here. So it's just for convenience. Here I check that either I is equal to 3, so that special case when I mean I equal to 3 means I don't put edge because it's already here. So either I is equal to 3, or let's ignore can function, or mask contains this bit. This bit is turned to 1. Okay. And can function is based on what I've read on input. It just says, can I go from this to here? So is it forbidden or not? The same thing for j. So j means iterating over edge that goes in, or maybe out, I don't remember. Now I write, if I is equal to j, I continue. This represents what I was talking about here, that I can't put an edge from 1 to 3 and from 3 to 1. So if both are equal and they are not 3, then continue. But they can be both equal to 3. It just means that I already decided about the 2 edges. And mask 2 is a new mask. So I have this mask currently describing some 3 vertices. I want to move to the next 3 vertices. So basically I will want to do mask 2 is equal to the previous mask divided by 4. But also I must change some bits. So for example, if I is different than 3, so if it's a real new edge, I just change some bit. So I just know, like I said that for myself that, for example, edge going out of 3 is 0, then going into 3 is 1, then 2, 3, 4, 5, something like that. And this, after deciding like this, I knew what is index of every bit. And I create a new mask, and basically then I do dp of this new mask plus equal the old number of ways. And so this is, and these few lines just try to avoid modulo. So this is equivalent to dp of mask 2 is equal to dp of mask 2 plus out of mask modulo mod. Just I want to avoid modulo to get a faster program, to get a better constant factor, because modulo is slow. And that's about it, but of course it isn't an easy program. Okay, so that will be everything for today. If you have suggestions, please write them in Codeforces topic about the stream. I do read everything, and I'm still not sure what I will do. I'm just trying to see what is fun for me and what is useful for people. So thank you everybody for watching, and I think the next stream will be on the weekend. I'm not sure about today, but it will be announced on Codeforces, and I guess again here it will be scheduled on YouTube. I'm not using Discord, and maybe I will start eventually, but so far I don't have Discord. So bye bye everybody, and see you next time.